Okay, class, again, good morning. So this is another topic in the fundamentals of thermodynamics. So last meeting, we already discussed about pressure. So we know already what are the different uh, pressure readings. So we know what is an absolute pressure, what is a gauge pressure, and what is a vacuum pressure. Okay. So by this time, we are now going to discuss about the temperature. So before we go, let us first define what is temperature. So temperature, of course, this is a measure of hotness or coldness of the substance or a body. Okay. So this is used to indicate the amount of energy with the molecules of the substance. So the international system of units, or in the English systems today, uses the Celsius scale. So formerly, the Celsius scale is called the centigrade scale. Okay. So of course, this is named after the Swedish astronomer Andre Celsius. Okay. Another is we have the Fahrenheit scale. So this is also named after Gabriel Fahrenheit. Okay. So the thermodynamic temperature scale in SI is the Kelvin scale. So this is named after Lord Kelvin. So the temperature unit on the scale is the Kelvin, of course. So it is designated by letter or capital letter K. The degree symbol was officially dropped from Kelvin in 1967. So you cannot say degree Kelvin, but a capital letter K only, or you designate only a capital letter K for a Kelvin scale. Okay. So the thermodynamic temperature scale in the English system is of course, the Rankine scale or Rankine scale. So named also after William Rankine or Rankine. So that is in 1820 to 1872. So the temperature unit of the scale is the Rankine, which is designated by capital letter R. Okay. Okay. So we go to the temperature measuring instrument. Okay, so how we are going to measure the temperature? Okay, for human body, we use the thermometer, of course, in order to determine the normal temperature of the body. Okay. So that is the common measuring instrument. It's the mercury thermometer. So we have also the so-called digital infrared thermometer. Okay. So that is another high-tech instrument. So used, of course, to determine easily the temperature of a body. Okay, so we have also the bimetallic thermometer. So this is like this. And another, we have the pyrometer. So this pyrometer is used in order to determine a temperature which is quite higher. And then we have also the so-called thermocouple. So there are several instruments that measures temperature. Okay, so we have the comparison of the two different temperature scales. So we have here the Celsius and the Fahrenheit scale comparison. Okay, so we know already that the boiling point of water is in Fahrenheit scale. Water starts to boil at 212 degrees Fahrenheit. In a Celsius scale, of course, that is 100. 100 degree or degrees Celsius. Okay. The freezing point, of course, this in this temperature scale, in Fahrenheit, that is negative 32. Okay? And in Celsius scale, that is designated as 0, meaning the water will start to freeze or starts to solidify at this condition or at this temperature scale. Okay. Okay, so this is another uh, arbitrary scale. Of course, the Fahrenheit and the centigrade or the Celsius scale. And we have also the so-called absolute value. So that is defined, of course, in English, that is defined in Rankine or Rankine, and in SI, we define that in Kelvin. So, as previously mentioned. Okay. So, how you are going to change, so for example, the Fahrenheit scale to Rankine scale? Of course, simple. So, if you have already a value of temperature in Fahrenheit scale, you just add 460, while for Kelvin scale, if you have already the Celsius scale, you just add 273. Or to be exact, that is 273.15. Okay? Or, yes. But how we are going to, let us go back to the arbitrary scale, the Fahrenheit and the Celsius scale. So by this time, we are going to derive a relationship between the Celsius and the Fahrenheit scale. So, knowing from the previous slides, the comparison of the two scales. So, we're in. So, as mentioned a while ago, that the water will start to boil in Celsius or in Celsius scale at 100. Okay. And solidifies at 0. And then in Fahrenheit scale, the water starts to boil at 212 and solidifies at 32. Okay. Let us now make an interpolation. Okay? An interpolation. Okay. So, ratio and proportion. Okay? So, the basis is, of course, the freezing point and the boiling point of the water. Okay. So, by interpolation, 100 minus 0. So, this is the freezing point or the boiling point minus the freezing point divided by the freezing point minus the temperature reading inside or between 0 and 100 as to 212 minus 32. This is again the freezing point and the boiling point minus or over the freezing or the boiling point minus the Fahrenheit scale between 32 and 212. Okay. So, by just manipulating the equation, so we arrive to an equation of, say, 21,200 minus 100 degree Fahrenheit minus 18,000 minus 180 degrees Celsius. Okay? So, rearranging the equation. So, that is 3, 2. Okay? So, combining constants. 3,200 minus 100 degree Fahrenheit minus or equal to negative 180 degrees Celsius. Okay. Dividing both sides the equation. Okay, so we divide both sides of the equation by 20 and then we arrive to an equation or a relationship of degree Fahrenheit is equals to 9 over 5 degrees Celsius plus 32. Okay. So we can also look the graphical presentation of the absolute value. Okay. So in this graphical presentation, we now see the comparison of the four temperature scales. Okay? So we have here the Kelvin scale and the Celsius scale, the Rankine, and the Fahrenheit scale. Okay. So, we have also here the term absolute zero. Okay, what is an absolute zero? Absolute zero is at negative 273 degrees Celsius. Okay. Take note. You cannot have a temperature lower than absolute zero. Okay. Absolute zero is the possible temperature that may be reached, of course. But below absolute zero, that is impossible. Okay. Another is absolute zero is the temperature at which the atoms are frozen. Okay? Meaning, the atomic movement or the molecular movement ceases at this point. Okay, frozen. Okay. So in Antarctica, the lowest temperature reading measured is only negative 89 degrees Celsius, or that is negative 129. Take note, absolute zero is negative 273 degrees Celsius. Okay, so it's quite far from negative 273 temperature in Antarctica. Okay, so example. So, based on the procedure on how you are going to devise, so for example, a new temperature scale. Okay. So in this example, so we have, okay, so let us now take this example. A new temperature scale is desired with freezing point of water at 0 degree X and boiling point occurring at 1000 degree X. Now, the problem is derive a conversion between degrees Celsius and degrees X, and what is the absolute value in degrees X. Okay. Solution, of course, by interpolation again. So, the same as the procedure and the derivation of the relation between the Celsius scale and the Fahrenheit scale. Okay. So, in degrees Celsius, or degrees, in Celsius scale rather, water boils at 100 and freeze starts or freezing is at 0. Okay? And in this new scale, the boiling point is 1000 and the freezing point is also 0. Okay, so by interpolation again, so we arrive to a relation of degree Celsius is equals to 0.1 degree X. Okay, so this is the relation derived. For the absolute value, so we have degrees X is equals to negative 273 over 0.1. So, in this equation, that is, the constant is 0.1. And we know already that the absolute value or absolute zero is at negative 273 degrees Celsius. So, substituting that value here, that is negative 273 divided 0.1, the absolute value is, of course, negative 2,731.5. Okay, so that is the example. If you are going to devise another temperature scale. Okay. Another example, we have here example number 2. During a heating process, the temperature of a system rises by 10 degrees Celsius. Take note, this is a change in temperature. Rises, meaning a change from an initial reading to a final reading. So that this 10 degrees is only the difference between the two temperature readings. Okay. express this rise in temperature in Kelvin, Fahrenheit, and Rankine. Okay, so solution. Take note that the change in temperature in Kelvin scale and in Celsius scale are the same. Okay. So, of course, that is 10 degrees Celsius is the same as with 10 degree Kelvin. Take note, this will only happen if the temperature is a change in temperature. Okay? Now, take note that for the absolute value in English, you will notice that the value in Rankine scale is higher as compared to the value in Kelvin scale. Take note that in the previous slides, in our derivation of the formula, we see that there is 5 and 9 in the equation. Take note that this 1.8 value here is the value of 9 divided by 5. Okay. In changing this, if you have already value in Kelvin or Celsius scale, just multiply it by 1.8, you will now get the absolute value or the change in temperature in Fahrenheit and the Rankine scale. So take note that 10 multiplied by 1.8, that is 18. Okay? So the change in temperature now in Rankine and in Fahrenheit is equals to 18 degree Fahrenheit. Okay? Okay. So that's all about temperature. So let us now proceed to the other topic. Okay? We have here the relationship of the force and mass. Okay, so this is from Newton's law. Okay. It states that, or this is the second law of Newton. So we know already. So what is this second law states? Okay. This states that if an unbalanced force acts in a body, the body will accelerate in the direction of the unbalanced force. Okay? And the acceleration will be proportional to the unbalanced force and inversely proportional to the mass of the body. Okay, so take note that this is the equation. Okay? The force is directly proportional to the mass and acceleration. Or simply, acceleration is directly proportional to the unbalanced force. So we are referring for the net force or the unbalanced force and inversely proportional to its mass. Okay? Okay. So although this topic here is very simple in SI units, so we have no problem for the SI. But take note that in our country, we are using different standards. Sometimes we use the English standards, we use the international system standards, we use also the European standards. Okay, so that's why this topic is very important. Okay. So there is a time that this formula can easily be computed. Okay. So take note that in the numerator, we have here the so-called the constant of proportionality. Okay? So the problem now is we have uh, two values for k here. One is a unity value and another is a non-unity. So we know already that if we say the value of k is unity, meaning the value of that is 1. So there is no problem in the calculation. But if the value of this k is non-unity, so if you if you do not consider in your calculation the value of that k, so there is a problem with the result of your calculation. Okay, so let us now proceed. In English, take note. In order to develop or produce a 1 pound of force, take note, that is 1 pound of force. The subscript F here represents a force. So in order to produce this 1 pound, it is required to move one slug of mass to an acceleration rather of 1 foot per second square. Okay? So take note. So in order to develop a force of 1 pound, it is required to move or to accelerate a mass of 1 slug to an acceleration of 1 foot per second square. Okay? In CGS units, this is centimeter, gram, seconds units. So that is CGS, centimeter, gram, seconds. We have another units or different units in English. Okay. The force in CGS is defined in dyne. Okay. How we are now going to develop or produce a dyne of force? Okay. So, in order to produce a force of 1 dyne, it is required to move or to accelerate 1 gram of mass to 1 centimeter per second square. So, if you accelerate 1 gram of mass to 1 centimeter per second square, the force now, or the unbalanced force acting on that particular body is, of course, 1 dyne of force. Okay? Okay. In MKS, what is MKS? MKS is meter, kilogram, seconds. That is MKS units. Okay. The unit in MKS, of course, kilogram, the force. And, of course, the mass is also in kilograms. Okay. Okay. So, by this time, the value of the constant of proportionality rather is no longer unity. So, but we have value. Okay. So, let's take a look at this now. Okay. So 1 kilogram of force, in order to develop a 1 kilogram of force or produce a 1 kilogram of force, it is required to accelerate 1 kilogram of mass to 9.806 meter per second square. Okay, so rearranging now the equation, the constant of proportionality here is equal to 9.806 kilogram mass. The subscript m here represents a mass. And then acceleration is meter per second. And here in the numerator, the subscript F represents a force. So take note. The force is different from a mass. Okay. Again, in English units, we have also a unit of mass in pounds. Okay. So previously, in the previous slides, we used the unit of mass as slug. So by this time, we now use the unit of mass as pound. Okay. So, in order to develop a force of 1 pound, okay, it is required to accelerate 1 pound mass to an acceleration of 32.174 feet per second square. So that is the required acceleration in order to develop a force of 1 pound force. Now, rearranging the equation or getting the value of the constant of proportionality, the value now is 32.174. Take note that the value in MKS of the constant of proportionality is 9.806 or 9.81. Okay? But here, we are now have a value of 32.2 or 32.174 pounds. Okay. So take note, this is another non-unity value. Now, in CGS, take note that previously, the unit of force is in dyne. By this time, we are now using the gram force. Okay? Take note, CGS is centimeter grams. Okay, we are now using the gram force here. Okay? So what is the required acceleration of 1 gram mass in CGS units? So that is 980.6 centimeter per second square. That's why the value of K now is 980.6 gram centimeter per gram force second square. Okay? So, there is a somewhat difficulty, of course, in calculation of the second law of Newton, especially if you are a beginner in this subject. Okay? Okay, so let us now proceed to the unit conversion. Okay? So, considering, of course, the value of unity, of the constant of proportionality K, okay, in the previous slides. So, this is in SI units. Okay? The value of K in SI is 1 kilogram mass meter per Newton second square. But that is only 1. In MKS, take note that the value is 9.806 gram mass meter kilogram force per second square. Now, so in this equation, we develop a conversion wherein 1 kilogram of force is equivalent to 9.806 Newton. Okay? And in English, so taking again this value of K in MKS and in English, so we also develop a conversion of 1 kilogram force is equivalent to 2.205 pound of force. Okay. And another we have here in English using the slug unit of mass. Okay. We also develop a conversion of 1 slug is equals 32.174 pound mass. And of course, in CGS, we also develop a conversion of 1 gram force equivalent to 980.6 dynes. Now, the question now is when the value of K is unity or not. Okay. Now, simply, or that is very simple, okay? Take note that if the unit of force is the same as with the unit of mass, take note, using the formula in Newton's law, or the force equals to mass multiplied by the acceleration over the constant of proportionality K. Okay. So, the value of K is non-unity if the unit of the mass and the force are the same. But if you are computing a force which is different from the unit of mass, say for example, the mass is in pound or in slug rather, and the force is in pounds, take note that the value of K is unity, or that is only 1. But if the unit of force is pound force and the unit of mass is pound mass, take note that K value is non-unity. Okay? So, I think that is clear to everybody. Okay, so let us now go to the mass and weight. So, this is another topic. Okay? Take note, okay. The mass of a body is the absolute quantity of matter in it, while weight is the force of gravity on the body or force exerted by the body against the ground. Okay? So, in this equation, the mass over the G, or the K rather, is equals to the force multiplied by the acceleration. This is equation from the second law of Newton. Okay? And that is also equal to Fg over G. Eh? Or that is the gravitational acceleration and the gravitational or the constant G. Okay? Take note that at the surface or near the surface of the earth, K and J are numerically equal. Okay? So, near the surface of the earth, K and G, or the constant of proportionality and the gravitational acceleration are the same. Okay? Okay, so let us now again consider a problem or an exercises about the previous topic, the Newton's law or the second Newton's law. Okay, so let us now consider this. A mass of 1 slug in space is subjected to an external vertical force of 4 pounds. If local gravity of acceleration is 30.5 feet per second square, and friction effects are neglected, determine the acceleration of the mass if the external vertical force is acting A, upward, and B, downward. Okay, so let us now consider the first condition. And using the equation on the second law of Newton. Okay? So take note that the direction of the force in the first condition is upward. And of course, the weight of the body or the mass is of course always in the direction of or in downward direction. Take note that weight is always towards the center of the earth. Okay? So, take note that the mass is 1 slug. Okay. So, by this time, we are now getting the value of the weight of the mass. Okay. That weight is same as with the force created by the mass. Okay. Which is equals to mass of the body multiplied by acceleration over the constant of proportionality, K. Okay? Now, substituting, take note here that the value of K is unity since the unit used by weight and mass are different. Okay. Take note that the weight or the force is in pounds and the mass is given in slug. Okay? Substituting the values, we get the weight of a mass of 1 slug equivalent to 3.05 pounds. Okay? Now, getting now the acceleration, again using the formula. So, by this time, we are now getting the value of the unbalanced force or the F net or the net force. Okay. So, since the direction between the two or the direction of the weight and the force applied is different, so we are going to subtract the two values. The 4 pound is upward and the force developed by the mass is 3.05, which is downward direction. So, subtracting the two, and then the mass of 0.01 divided by the mass of 0.1 rather, the acceleration now is 9.5 feet per second square. Okay? Same as for the condition at B. So, the condition of B is that the force and the weight are in the same direction, or that is downward. Okay? So, if the direction of the weight and mass are the same, of course, we are going to sum up the four found force and the 3.05 pounds. Okay? So the acceleration now here is 70.5 feet per second square. Okay? Again, we have a relation between the weight on Earth versus the weight on Moon. So in this case, consider the mass on Earth equal to the mass on Moon. So this is the principle. Uh, the weight on Earth is the same as the weight on Moon. Okay? Excuse me. Okay, so weight on Earth is equals to mass on Earth multiplied by the gravitational acceleration on Earth. Okay? And the weight on Moon is equals to the mass on Moon and the gravitational acceleration, of course, the Moon. So knowing that the mass on Earth is the same as with the mass, of course, at the Moon. Okay? So equating now the two equations, we arrive to an equation which is equals to the weight on Earth over the gravitational acceleration on Earth is equal to the weight on Moon over the gravitational acceleration on the Moon. Okay? Okay, so let us now again go to the other fundamental principles or fundamental topics in thermodynamics. Okay? We have here the specific volume. So we know already that specific volume is just equal to the reciprocal of the density. Okay? So we know already that in this equation. So that is very simple. So take note that we have here a constants for volume. So in English units, MKS and SI. Okay? So in English, we have 1 cubic foot equals to 7.481 gallons. And 1 gallon, of course. So in MKS, that is 28.317 cubic centimeter. And 1 gallon, 3.785 4 liters. Okay. So we have 1,000 liter in MKS, that is equivalent in SI to 1 cubic meter. 1,000 cubic centimeter, or that is equivalent to 1 liter. And take note here, 1 drum is equivalent to 55 gallons, so that is for petroleum, so unrefined. And 1 barrel is equivalent to 42 gallons. Okay? So refined petroleum products and other liquids. Okay? We have also the relation between the weight, density, and specific weight. Okay? So the weight density, or the unit weight, is equals to the force or weight over the volume. Okay? Or simply, force or the weight is equals to mass multiplied by gravitational acceleration. Okay. So that is equals to, knowing that mass over volume is equals to density. Okay. So we arrive to this equation. Okay. So take note, 1 slug is 32.174 as previously derived. Okay. In MKS, same relationship. Okay. In SI, same relationship. Okay. So what is G sub O and G sub C? Take note that G sub O is the observed gravitational acceleration and the G sub C is the constant of proportionality. Okay, so take note that if the body is, of course, near the surface of the Earth, the value of that are the same. Okay. Another, we have the specific gravity and the relative density. Okay, so specific gravity, take note that this specific gravity is based on the, for liquid, that is based on the standard liquid. Okay, so that standard liquid is of course the water. Okay, so that's why we have here, that is the density of the substance over density of water. Okay, so for solid and liquid. Okay, so for gases, that is specific gravity is equal to the molecular weight of the gas over the molecular weight of the air. Okay? So the standard fluid or gas is, of course, the air. Okay. Okay. So let us now consider this example. The mass of air in a room of 3 meters by 5 meters by 20 meters is known to be 350 kilograms. Determine the density, specific volume, specific weight of the air. Okay? So knowing that density equals to mass over volume, and the mass is given, we have 350, and the volume, of course, is multiplying the 3 multiplied by 5, or the height, the width, and the length. So the density now is 1.167 kilogram per cubic meter. And knowing that the specific volume is the reciprocal of the density, okay, 1 divided by that density, of course, 0.857 cubic meter per kilogram. Okay, so knowing also that the unit weight, okay, so that is 1.67, multiply it by 9.81. Okay, so that is defined in Newton. Okay, kilonewton per cubic meter. Okay, 11.45. Okay. Another example we have here, a tank contains a mixture of 20 kilograms of nitrogen and 20 kilograms of carbon monoxide. The total tank volume is 20 cubic meter. Determine the density and specific volume of the mixture. Okay, solution again. Density equals to mass over volume. So, since this is a mixture, so we add the 2. So, and the volume is 20. So, therefore, the density is 2 kilogram per cubic meter. Again, specific volume, the reciprocal of density, that is equals to 0.5 cubic meter per kilogram. Okay? Another example. So, two liquids of different densities. Density 1 equals to 1,500 kilogram per cubic meter. And density 2 of 500 kilogram per cubic are poured together into 100 liters tank, filling it. Okay. If the resulting density of the mixture is 800 kilogram per cubic meter, find the respective amounts of liquid used. Also find the weight of the mixture. Okay. The gravitational acceleration 9.675 meter per second square. Okay. So, in the condition, in the problem, the total volume is, of course, the summation. The volume 1 plus the volume 2, which is equal to 100 liters or 0.1 cubic meter. And, of course, the mass or the total mass is equal to the summation of course, masses. Mass 1 plus mass 2. Or the density of the mass total is, of course, density equals to the mass over the volume. Okay? Okay. So, the mass now is 800 kilogram per cubic meter multiplied by 0.1 cubic, that is now 80 kilograms. Okay? So, continuation. Also, the mass is equals to mass 1 plus mass 2. So the total mass is 80. So knowing also that mass equals density is equals to mass over the volume, or the mass equals to density times volume 1 and density 2 volume 2. So we arrived to a value of the volume was equivalent to 0.3 cubic meter. Okay? So the mass now of the first liquid, so knowing the density and the volume, so that is equivalent to 45 kilograms. And the mass too, of course, is 500 kilograms. And the weight of mixture, of course, is knowing the equation, weight is equals to mass times the gravitational acceleration, that is now equivalent to 774 Newton. Okay? Another, we have the conservation of mass. Okay? So, law of conservation of mass states that the total mass is constant or indestructible. Okay? So, at any point, of course, along the stream, in this figure, the mass is considered constant. Okay. So, considering the continuity equation. Okay? So, Q, or the discharge, is equals to cross-sectional area multiplied by the, of course, velocity of the fluid flowing inside the pipe. Okay? So that is, of course, at any point. Okay? So, specific volume again, the same. Okay? 1 over the density. So, take note, this is for a liquid fluid, of course. Okay? So, this is a liquid. For gaseous fluids, we always consider the density of the gas at any point. Okay? So, the equation from continuity equation, multiply it by the density that is applied to a gaseous, okay, substance. Okay? Okay, so let us now consider this example. A pump discharges into a 3 meter per side cubical tank. Okay, cubical tank. The flow rate is 300 liters per minute and fluid has a density of 1.2 times that of water. Density of water equals 1,000 kilogram per cubic meter. Determine A, the flow rate in kilogram per second, and the time it takes to fill the tank. Okay, solution. So since the tank is cubical, so the volume, of course, is the uh, product, of course, of the three sides, okay, which is 27. That is 27 cubic meter, not 37, okay? So, the discharge now is 300. So, changing it to kilogram per seconds, the value is 6 kilogram per seconds. Okay. And the time now required, of course, is the volume divided by the discharge. Okay? So the volume is 27 cubic meter divided by 0.3 cubic meter per minute. The resulting value now is, of course, 90 minutes. Okay? So, I think example now are very sufficient for you to know how you are going to calculate the fundamental principles in thermodynamics, such as temperature, the first or the second law of Newton, the weight, the relation of the mass,
the discharge, and so on and so forth. So, it is very now sufficient. Okay, so examples are very well explained uh, for you to master the subject in thermodynamics. I think so. This is the last slide. So, thank you very much, class. Okay?